Hello, physical science students. I am going to cover Chapter 5, Heat and Matter problems, and I'm going to start with just some temperature conversions. So the first problem I want to look at is right here, and it's to convert 97 degrees Fahrenheit into Celsius. So I have written our formula here. Degrees Celsius is equal to 5 divided by 9 times the degree Fahrenheit minus 32. And since this is in parentheses, we must do that first. So we simply plug in 97 Fahrenheit minus 32 and do that calculation and then multiply by 5/9. And when we do that, we get 36.1 degrees Celsius. So the temperature equivalent of 97 degrees Fahrenheit in Celsius is 36.1 degrees. So the only trick to this one is knowing and remembering to do what's in parentheses first. Let's look at the second one. We're going to convert now what we just had, 36.1 degrees Celsius, and we're going to turn it into Kelvin. Remember, Kelvin is just another temperature scale we use, and we can think of it as a temperature scale of convenience. We can also think of it as the absolute temperature. So what is our formula? Kelvin is however many degrees Celsius you have, you simply add 273 to it. It's that simple. So Kelvin then is 36.1 degrees Celsius. That's what our problem is giving us. And when we add 273 to that, you get a temperature, an absolute temperature of 309.1 Kelvin. Now let's do one converting Celsius into Fahrenheit. Okay, so I'm giving you that 36.1 degrees Celsius and we want to convert that into Fahrenheit. So the formula is 9/5, 9 divided by 5, and then you multiply that by your degrees Celsius plus 32. So plugging all of that in, you can put in 9 divided by 5 and get whatever decimal that is, multiply it by 36.1, and then add 32, and voila, we get 97 degrees Fahrenheit, which is exactly what we started up here at 97 Fahrenheit, which converts to 36.1 Celsius. So 36.1 Celsius should convert right back to 97 Fahrenheit, and in fact it does. Now we're going to do a heat transfer problem. And the equation for heat transfer, and we use the symbol Q for heat transfer, is equal to the mass of the substance that you have times its specific heat, which we can look up in a table in a book, and times delta T, which is simply the change in temperature you're wanting to happen. So we can shorten that formula to Q equals MC delta T. So here's a problem for you. If you have 0.005 kilograms of a substance, that's its mass, kilograms tells us that, and you're given that the specific heat of that material is 2.01 kilojoules per kilogram degrees Celsius, and you want a temperature change, a delta T of 10 degrees Celsius, the question is how much heat needs to be added to that substance for that to occur. So in this case, we have mass 0.005 kilograms, specific heat at 2.01, and delta T at 10 degrees. So you just plug in the values into this formula right here, and you get your heat content of 1,005 kilojoules of heat would be required to get a 10-degree temperature change of that substance, which has a specific heat of 2.01 kilojoules. Let's do another heat transfer problem. And in this case, we have, let me grab a pen here, I must have lost it. The problem says, what is the mass of a substance whose increase in heat content is 0.045 kilojoules, and you want a 2 degrees Celsius temperature change. Specific heat of the material is 0.780 kilojoules. So in this case, we're still using this heat transfer problem up here, but we're going to solve for mass. So rearrange it, and solving for mass, we would have to divide by specific heat and the temperature change. So you get the heat content divided by specific heat times the delta T. Let's plug in our numbers. All right, they give us the heat content of 0.045 kilojoules. So we're going to put that right there. And then they give us the specific heat of 0.780 kilojoules. And then our temperature change, delta T, is 2 degrees. And when you put that into your calculator, you will get 0.029 kilograms. And if they wanted that answer in grams, you would simply multiply by 1,000, and that would be 29 grams. One note here, the specific heat is reported technically as kilojoules per kilogram degree Celsius. Oftentimes it's just shorted to kilojoules. But if you're looking to balance all those little units when you're in your calculation and have them cancel, you need to keep that kilogram degrees Celsius as part of your specific heat. So I heard you ask that you need one more heat transfer problem. So let's do this once again. Oh, let's pick red for our color. And here's our problem. What is the specific heat of a 0.005 kilogram substance that gains 0.05 kilojoules of heat, and you have a temperature change, a delta T, of 6 degrees? So here we're asking for specific heat. So we're going to have to rearrange this formula here and solve for C, the specific heat. When we do that, we get the heat content Q divided by mass times delta T. So let's go back up to our information in our problem and plug in the values. Specific heat is equal to the heat content, 0.050 kilojoules, divided by the mass. Kilograms tells us mass, so 0.005 kilograms. And then our delta T, our change in temperature that we want to occur, is 6 degrees Celsius. Plugging all those into your calculator, you will get 1.6 kilojoules per kilogram degrees Celsius. Once again, this is technically the units for specific heat. Oftentimes it's just reported as kilojoules, but keep that in mind. Technically it's kilojoules per kilogram degrees Celsius. That should be enough for heat transfer problems. Let's move on to something else. Let's talk about the gas laws. We're going to start with Boyle's gas law. And Boyle's gas law, if I can talk, says the pressure and volume of a gas are inversely related. That means as pressure increases on a gas, its volume will decrease. And logically, that should make sense to you, because the gas molecules are so far apart that when you compress it, it's easily compressible. Gases are easily compressible due to the fact that their molecules are far apart. So let's go back here. According to Boyle's gas law, the pressure P1, V1, pressure times volume, in case number 1 should equal the pressure at case number 2 times volume 2. So oftentimes we just write P1, V1. Pardon my chicken scratches. It's hard to use this pen sometimes. P2, V2. Okay? So here's our problem. The initial gas pressure is 200 kilopascals. Our units for pressure are pascals, and in this case we're using kilopascals. So that's our initial gas pressure, P1. And the initial volume is 10 cubic meters. And then we're going to increase the pressure 4 times, from 200 to 800 kilopascals. So our new pressure at P2 is going to be 800 kilopascals. So the question then becomes, what is the new volume of the gas at that new pressure? So yes, you can absolutely rearrange this equation and solve for V2. So V2, volume 2, is equal to pressure 1 times volume 1 divided by pressure 2. And you can plug in those numbers. So pressure 1 was 200 kilopascals. And the volume of volume 1 is 10 cubic meters, which goes there. And then we're going to divide that all by the new pressure of 800 kilopascals. And when you punch that in your calculator, you will get 2.5 cubic meters. Now, if you understand what an indirect or inverse or indirect mathematical formula is, you wouldn't have even had to plug those numbers into that. Because if you increase your pressure 4 times, that means your volume should become a quarter of the amount. And in fact, it does. 1/4 of 10 is 2.5 cubic meters. So if you want to prove it to yourself, absolutely put it in the formula and solve. If you understand that indirect inverse relationship, then you can simply do the math in your head. An increase of 4 will become a quarter of the amount. Let's continue on with the next gas law, and that is Charles's gas law. The formula is the volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. So right here. Now, Charles' law says that the volume of a gas is proportional, directly proportional to its temperature. So what that means is, as temperature increases, those little gas molecules are going to move faster and therefore expand out further, and volume becomes greater. Okay, so let me go up here and get a pen. Well, that's not a fun color. Let's pick green. And here's our problem. The initial volume of a gas, V1, okay, is equal to 10 cubic meters. Cubic meters is the unit for volume. And the temperature, the initial temperature, is 100 degrees Celsius. And then the temperature of the gas goes up 4 times to 400 degrees Celsius. What's the new volume? So we're solving for volume 2. So let's rearrange the equation. And when you do that, volume 2 is equal to volume 1, or V1, times T2 divided by T1. Plugging in those values, the initial volume, 10 cubic meters, the final temperature, temperature 2, 400 degrees Celsius, divided by the temperature of 100 degrees Celsius, which was the initial temperature, temperature 1, and you get 40 cubic meters. All right, now let's think about that. If our initial volume was 10 meters and our initial temperature was 100, and we understand what a direct proportional relationship is, if we quadruple the temperature, then the volume should quadruple. And it does, from 10 to 40 cubic meters. So once again, you didn't really need to plug all this in, but if you want to prove it to yourself, absolutely, you can do that. I think I'm going to stop here, and our second video will cover pressure, density, and heat engine efficiency.